some kind of detection indicator on that interface.
All right, let's get started then. Let me open up chat again. There we go. Because I can't do both crap. All right, so I'll check chat every once in a while. For some reason, I can't keep chat open while I have the screen on. So we'll just play it by ear. Anyways, chapter 25, electromagnetic waves. I'm sure you guys are all aware of what an electromagnetic wave is. The most common use of them, of course, would be color, the visible light spectrum. We talked about this in lab a bit, how the different colors that we saw through those gases are in fact different lengths of wave. Here's an example here shows that difference. We've all seen this stuff before in physics, I'm sure. We're going to do it deeper here. So we'll talk about the production of electromagnetic waves, the propagation of electromagnetic waves, the EM spectrum as a whole, energy and momentum in it, and some polarization. Lighter on the math side of things than we've seen before. Shouldn't be too bad. Should be somewhat enjoyable. This stuff's kind of fun. So, what is an electromagnetic wave? How are they produced? Well, they're produced by an oscillating charge. We see here, you guys recognize this symbol here. This is the AC generator symbol, right? This purple guy. And what's AC do? It oscillates a signal back and forth. So if you have some energy here, time being on the x-axis here, if you have some energy here, this oscillation switches back and forth, causing that charge, whatever that charge may be, to move up and down. This oscillation involves some amount of energy over some amount of time, producing a wave. Right? This text goes over that. Remember, these slideshows are on Canvas. You can download them, look it up a bit better if you want to. But an AC generator is a good analogy for electromagnetic waves. Electromagnetic wave propagation is in the positive x direction. And here you can see the electromagnetic fields due to that propagation. Again, we're following the right-hand rule here, right? This propagation follows and switches back and forth as the particle goes up, down, left, right, what have you. Cool side effect, we're kind of tying a bunch of different classes together, I would argue. And yeah, pretty, right? I'm trying to say here is we've talked about all a bunch of things prior to this, AC generation, right-hand rule, movement of energy, momentum, things like that. And it's all sort of coming together here with electromagnetic waves. The direction of propagation, the directions of electromagnetic fields, electromagnetic wave, said use the right-hand rule. These slides are, I'm kind of explaining the slide before it gets to that, but yeah, we've seen that before. At any time electric charge is accelerated, it radiates, and this accelerated charge radiates electromagnetic waves, right? So you move a charge back and forth. What happens? The energy leaves that moving charge and following right-hand rules, and we can see that effect via what we call radiation. Radiation is, when you think of radiation, you probably think like the Incredible Hulk, things like that. Truth be told, radiation is a very broad term that in pop culture has like one specific meaning, but radiation is the propagation of energy, essentially. Light, by definition, is a radiation. Right? All electromagnetic waves propagate through a vacuum at the exact same speed, the speed of light, which is 3 times 10 to the 8th meters per second. You're going to commonly see that in literature as 3e to the 8th, e being times 10. And that is a number that, honestly, it's what hurts you just to know. It's very useful information. So that is the top speed of the radiation of electromagnetic radiation, light being one of those. All of the EM spectrum moves at this exact speed. which is here 3 e⁸ meters per second. If you are not in a vacuum, light moves slower. We talked about that a bit, why we'll get more into later. But as you get a more dense material, air, water, light slows down. The speed of light is stupidly big, right? 3 e⁸ is a massive speed. The first measurements were done in the late 1600s using the eclipses of the moon of Jupiter as a way to propagate and understand the speed of light. We have more, obviously more correct measurements nowadays, but again, ridiculous. You can look at Jupiter being that far away and you can measure these. You can use the eclipses of the moons of Jupiter to measure the speed of light. It's cool stuff. That's of more interest to you. I'm sure there's some documentary on YouTube you could read about it. We're not really too interested in the history in this class, right? The first laboratory measurements of the speed of light were done by Foucault. I'm going to guess that's how it's pronounced. Foucault in the later part of the 19th century, using a notched wheel and sending light bouncing back and forth to a mirror. And then the speed of that notched wheel, he can accelerate that, use some math, we'll do an example here in a bit, to figure out how fast the light is going based on if you can see the notches in the wheel or not. It's some pretty basic math that provides you very interesting answers to questions. And you can kind of picture this, right? If you open and close something, right, you're going to see your hand. But if you do it fast enough, you won't. I'm sure you've seen videos where the shutter speed of a helicopter, the shutter speed of the camera, there we go, is the same as the rotation of like a helicopter's blades. So much so that on camera, it looks like the blades are not moving because the shutter of the camera is closing at the same speed as the blade is doing one complete rotation. If you've never seen that, look it up real quick. It's cool stuff. But this base concept is used here to measure the speed of light. And the value of the speed of light is given by this electromagnetic theory here. It comes out to 3 e⁸ in a vacuum. But those two constants, this epsilon naught and this mu naught, are numbers we've already seen before, right? Numbers we've used for electricity. And we're going to use them again here because, well, electricity, magnetism, these are all very similar components, right? Very large scale speed, very fun stuff. Speed of light is 3 e⁸. A light year is how long it takes light to reach us. So when you look at a picture from, let's say, the Hubble Deep Space Telescope, you look at all these images, it's kind of absolutely ridiculous to think how long that light's been traveling through space to reach us, right? The light from the Andromeda galaxy here on the left takes about 2 million years to reach us. So when you look at the Andromeda galaxy, you can see the Andromeda technically with your bare eyes. It's bright enough. A telescope's obviously better. But if you look at the Andromeda, you're looking at a picture that was taken 2 million years ago. That's pretty nuts. So let's do an example here. I'll give you guys a little bit of time to write this stuff down if need be. This is straight from the book. If you got the text open, that works too. I'm just going to kind of walk through it because can I see your other? No, I can't really see other ones, can I? Crap. Okay. Since I can't see what you're doing, I'm going to kind of just, as I said, walk through it. We'll see how this works. Hopefully this works out well. You make this, step back real quick. You make this right here, this component. You create this experiment. And what you do is you create that experiment with a 450 notch wheel. So there's 450 of these little teeth in this wheel. You spin that wheel at 35 revolutions per second. So every second, that 450 notched wheel rotates 35 times. You place a mirror 9,000 500 meters away from this wheel, big number, right? And you watch the light bounce. And what you notice is that the light is able to strike the mirror and bounce back in the time it takes this guy here to go through one notch. Exactly one notch. That's what you notice. Using this information, can you calculate the speed of light? Yes, very much so. If you know how long it takes to skip each notch, you can figure out the time it takes for the mirror, the light to bounce back and forth, right? And then you have a distance, you have a time, a velocity is easy to calculate, which is what we do here. The time it takes something to move in this rotational manner, we talked about rotational speed last semester, is equal to theta here, which is the arc length, the distance between the notches, divided by omega, which is the rotational speed. This is a distance over speed to give you time equation. And you come up with about this tiny amount of seconds here, is the amount of time it takes for each notch to pass perfectly. Take the amount of time, plug it into d divided by t, you get 3e to the 8th. And you can YouTube examples of these people doing these exact experiments, getting these exact results. This O thing here, that's supposed to be an omega, the angle sign. And I watched a video, I would have shown the video in class, but I watched a video of a guy that did this on a beach, and he measured the speed of light on a beach using this exact setup. It was kind of ridiculously cool. But yeah, like I said, this slide shows on Canvas, including these examples, if that helps at all. And, just contact me via email as we're going through the questions, what have you. We'll get through it. All right. So hopefully that was understood well enough. It's basically distance. It's basically a velocity equals distance divided by time equation, but you can do a lot of interesting science to figure out these seemingly complicated questions. All right, let's go to propagation of electromagnetic waves. Let's talk the Doppler effect. You know the Doppler effect with sound, but the Doppler effect also happens with EM radiation, in such that the speed of the waves in a vacuum do not change, but the observer and the source move with respect to one another, so the frequency does change, right? Doppler. We talked about Doppler. That's what Doppler is. This is actually going to tie into modern physics when we talk about length and time dilation, which is cool. But since these are essentially, we talk about EM spectrum as waves of energy, Doppler effect works. Because all electromagnetic waves have the same speed in a vacuum, the relation between the wavelength and the frequency is shown here. The speed is equal to the frequency times lambda, which is the wavelength. And we finally jumped into it. Down here, this bar shows you the known EM spectrum. Down here, radio TV waves, they're commonly called radio waves, not TV waves. But we notice here, these have a very low frequency and a huge wavelength. And what you need to do is remember the speed of light is 3e to the 8th. So at 1 meter of wavelength, you're at about 3 times 10 to the 8th frequency. So this math works out beautifully. Radio waves are gigantic. We'll get into it in a bit, but the reason why you can listen to an AM station from like Minneapolis, but you can't listen to a Marquette station on FM is because AM stations are right down here with gigantic wavelengths. So they're able to jump large swaths of land without getting caught up in buildings, hills, what have you. FM stations, contrary, even if the power is greater, get soaked up by stuff because they can't travel through it as well, right? So you don't get FM stations as far away. Up from radio, you got microwaves. This is what your microwave uses here, microwaves. Infrared or IR, this is the heat signature waves that we see, right? Visible light band, the colors of the rainbow, Roy G. Biv. showing this little tiny swath between infrared, below red, and ultraviolet, above violet. UV is what we protect our UV rays, or what we protect our skin from the sun from. Pretend that sentence made sense. X-rays, you know what those are, especially all you people being bio majors. And gamma rays, which is the Incredible Hulk, or in the real world, lots of gross cancer. Of course, I jumped the gun a bit and skipped over what we're talking about in these slides. Fantastic. You can go back to this if you want later, but radio waves, lowest frequency, microwaves, low higher frequency, smaller wavelengths. These things go stupidly big wavelengths, getting smaller and therefore higher frequency, because all these numbers need to add up to the speed of EM radiation, the speed of light. So higher frequency, right? Higher frequency times smaller lambda, smaller wavelengths, always going to give you 3e to the 8th speed of light. IR, this is what we call heat, is actually infrared radiation. Cool story. When you look at a picture like this, that's not actually the colors of infrared radiation. That is simply a computer algorithm saying the hotter it is, we're going to call that white. You could swap these colors, make them whatever you want, and you'd still get the same effect. It's the intensity of the radiation that makes these colors special. So infrared isn't purple to white. It's just what we call it, if that makes sense. Visible light, I'm sure you're familiar with that. UV here, tanning, burning, skin cancer, stuff like that. Funny enough, again, as you guys are bios, you should understand this. Animals can see outside the visible light spectrum. Insects use ultraviolet light to, for example, notice flowers. It's crazy if you look up a video of like a bee's point of view as it flies. It's just ridiculous, the extra detail of visible if you can see outside of our narrow band that our eyes allow. I think like octopuses can see beyond our light spectrum and stuff like that. It's pretty cool stuff. X-rays used mostly for medical imaging, as we know. X-rays work because an X-ray will go through the flesh but won't go through the bone. So bone shows up as a dark, which then we convert to a white so that we can look at bone structure, see if something busted. Very useful stuff. And of course, gamma rays, these kill you dead, or if you're incredibly lucky, turn you into the Incredible Hulk. Badoom-tish. Extremely energetic, destroy things that they go through. And why do they destroy it? Because they're oscillating so fast that your skin doesn't have time to recover, doesn't have time to reconstruct itself, and actually burrows holes through your cells and things of that nature. Not good stuff. Sweet. So talked about EM spectrum, talked about the different chunks that we separate it into. Those chunks are more or less rules of thumb, not necessarily anything too specific. Something very low on the X-ray spectrum may not be as good as X-rays as something in the middle. It's variable, right? But let's take this concept and throw it back into our classical physics, into our energy and momentum conversations. So an electric field has some energy density to it, right? E being an electric field, epsilon naught being a constant we've talked about before. I think that's the 4 pi times 10 to the -7th. I'm going to have to, we'll get to an example that uses it. And then this little u, I don't know if that's a Greek letter or just a lowercase u off the top of my head. Sorry. We'll call it a lowercase u for now, is the energy density of electricity and magnetism. Again, notice these are different constants. This is a constant associated with magnetism. This is a constant, epsilon's associated with energy. And if you know the energy density of these particular fields, you can figure out the total energy density of a electromagnetic wave. Why are only these two, electricity and magnetism, the things we care about to figure out energy density? Because if we go way back, right-hand rule says as a velocity travels in a certain way, a right-hand rule, the point and the curl will give us energy and magnetic fields. These are perpendicular to each other, and they are the things that are produced when a charged particle travels, right? So those are the things we care about for the energy of an electromagnetic wave. The energy densities and electromagnetic fields are equal to one another, which is cool, right? Because again, they're equal in intensity and perpendicular in direction. You don't for some reason get more electricity than magnetism from a wave. They're tied together. They're intrinsically linked. They're right-hand ruled. You can't break the right-hand rule. It's not going to happen. So we can take this big, gross, nasty equation. That is, in fact, a big, gross, nasty equation. And we can chop it up into little teeny, tiny bits, giving us energy is equal to the speed of light times the electric field is equal to the speed of light times the magnetic field. There. This equation looks a lot nicer than this equation. You probably don't want this. You probably want this. But I'll make you use both because I am a mean, terrible person. The energy a wave delivers to a unit area in a unit time is called the intensity. You can kind of consider this the pressure equivalent, right? Because it refers to area and time. And we call that intensity. How intense a flashlight is directly proportional to how far away you are from the light, how strong the light is, and how long it's been staring at you, right? If I flash a light into your eye right away, you can get the area that the beam hits you is going to be very small, so it's going to seem a lot brighter than if you're on the other side of the football field. This makes sense in a practical way, but now we have math to go about it. This big, gross, nasty math. So let's talk. Let's talk example. 50-watt bulb. This 50-watt bulb illuminates a garage. You've been in a garage. Garages have light bulbs in them. Sweet. Given that information and the fact that 5% of that 50 watts is used by the bulb to produce light, which means of that 50 watts, 95% of that actually is shown as light. The rest of it is used by the bulb. What is the average intensity of the light? And what is the EMS electric the RMS electric and RMS magnetic fields a meter away from the light bulb? How do you calculate this stuff? Well, use the equations we had before, plus some equations from a couple chapters ago to figure it out, right? Because we're talking average intensity, we're talking capital I here, which relates these guys and those guys come into play from these guys. So the average intensity is equal to your average power, PAV. These AVs are supposed to be really small at like, where you at? Like how this RMS and this AV is really small. It's supposed to look like that, but I couldn't figure out how to subscript in Google Slides, so I'm just going to explain it. Sorry. Your average intensity is equal to your average power divided by your area. In other words, it's a pressure equation, right? So we take 50 watts, multiply by 0.05. This is going to give us the amount of power that the bulb is actually using. And then we're going to divide that by the area. It's a light bulb. It illuminates in a sphere, right? So we're using 4 pi r squared here to define the area. And we get a number that looks like this. Pretty straightforward, not too bad. But energy RMS and magnetic field RMS sounds scarier, right? Well, let's take a look. We can get the energy RMS by using this equation. I'm going to skip back to show you where the equation came from real quick. Right here. Energy given by this guy, energy given by this guy. And then RMSs show up from here. So, since we know the intensity release, We can use C times epsilon. It's supposed to be epsilon naught. Again, I couldn't figure out subscript, so it'll work. C times epsilon times the energy RMS. This right here, E RMS squared, E RMS is what we're actually wanting, right? This is the equation here. The numbers placed in the same order as shown up here. And then you need to solve for this guy here. So, you know, this equation is done in the book where it solves the equation for ERMS first, but it was a huge hassle to put in the slides. The equation writing in slides is horrible. So this is math you guys can do, right? Divide this, divide that, square root, 8.66 newtons per coulomb. Cool. Energy, newtons, electricity, coulombs. Makes sense. Magnetic fields, RMS, follows a similar yet different equation where the speed of light times the magnetic fields, RMS squared, divided by mu. It's supposed to be, again, mu naught, technically. There's your 4 pi times 10⁻⁷. Math you can do. Math I don't need to explain to you. Divide over, multiply, square root to give you this Tesla. What this is telling you is, remember, all electromagnetic energy has an electric and a magnetic component to it. However, if we notice here, this light bulb technically has magnetism. It's releasing a magnetic field, but 2.9 times 10 to the negative 8th Tesla is inconsequential. Very tiny magnetic field. Nothing. You don't have to worry about your keys flying out of your pocket and going to hit the light bulb, right? It's a very small magnetic field. Technically, it exists, but it's very tiny. More examples of equations we can do. If we substitute energy density into the intensity equation here, we can figure out a momentum that's associated with electromagnetic fields. So we got mu c, which is, as we remember from the adding up the energies available, electromagnetic energies add up this way, divide stuff out. We can find an equation for the momentum of an electromagnetic field, which is the U. The book uses U to mean potential energy. Remember that, divided by the speed of light. So the amount of energy something has divided by the speed of light tells you its momentum. Speed of light is used everywhere. The deeper you get into physics, C just randomly shows up everywhere. It's pretty impressive. But yeah, big, nasty equation, very simple concept at the end of the day. Since these EM spectrums exert a pressure, they call it radiation pressure. And this radiation pressure is responsible, for example, the curvature of a comet's dust tail. This EM spectrum is moving out. Since something's actually moving, it has a pressure to it, it pushes. Even if it's just a few particles in a otherwise basic vacuum, those particles still have some effect. Another cool example of this pressure would come from, I think we've talked about this a bit, but one of the examples that of how we want to travel long distances in space instead of using jet fuel and rocket fuels and rockets and stuff like that is essentially to sail through space. You can create a satellite, for example, put large, I think, silver and gold foil fans around it, and those fans will actually be contacted by ions and EM radiation being released from stars and planets and stuff like that. And since those EM radiations have some pressure, they apply a force to the fan and the satellite will actually start flying. And it'll keep going faster and faster and faster as long as radiation's hitting it. Because remember, these particles are moving 3 times 10 to the 8th meters per second, moving really, really fast. So while they're really tiny, can't exert a lot of pressure, they also hit really hard. And over time, something can get going incredibly fast, essentially sailing in a vacuum. Very cool concept. I think there's been calculations that something can get to like a third the speed of light doing this. Just amazing stuff. Again, YouTube it if that's of interest to you. You can find videos of future ways to travel the stars and stuff. It's fun stuff. All right, let's talk polarization. I'm sure you all have a pair of polarized sunglasses. Polarization is, well, that's what we're going to talk about. So the polarization of an EM wave versus the direction of its electric field. As shown here in A, this is polarized in Z direction because electric field is perpendicular to the X and the Y. However, since this electric field follows the right-hand rule, it can be twisted and turned all around based on many different circumstances, based on if there's a pole to one side or the other for the electromagnetic fields, relationships, other things, or as we get to, polarizing lenses and filters. So since polarized light has its electric field all in the same direction, unpolarized light, by definition, has electric field in randomized direction. Here we have some vertical polarized light. The particle is propagating along the purple arrow, and every part of this particle is oriented in the same direction, giving you a polarization up and down. However, if that's not the perfect scenario, nothing's ever really perfect, right? You can get an example here where the particle may be in some version of twisting, we'll call it doesn't actually twist, but some version of twisting, so much so that the electric field, and by definition the magnetic field, is in any various direction. It's unpolarized. When you look at light, you're looking at B. A, we'll get to how you make A. So what can we do with this information? Well, let's take an example of a string, right? Because these electric fields essentially wobble up and down, as we talked about previously at the start of this chapter. And what can you do about that? Well, if you've got something that's wobbling up and down, you don't want to wobble up and down, don't let it wobble up and down. You can create small slits, small filters, small lenses that have such tiny separations between what the light can go through and what the light can't go through, a light in a dark section, if you will, that it will prevent light that is not polarizing in the direction that you want to polarize. As shown here, you got the string moving up and down. Well, if you try to send this string through this bottom B slit here, it's not going to move up and down. It's going to be stopped, and you're going to lose this up and down effect, right? In essence, this is a way to take light that is polarized in many different aspects and turn it into light that is polarized in a way we want. Here we have a polarizer. This is a lens, essentially. And what it allows you to do is light will enter it in whatever field it wants, but light will only exit along the direction of the polarizer, along this black line here. As you can see, the propagation direction shown after the polarizer is the same direction as the polarizer itself. And the mechanical analogy explains how this can work. Since the electromagnetic fields only go in a certain direction, the light's only vibrating, the EM radiation is only vibrating in a certain direction. If you don't allow it to physically move through the object in that certain direction, then it won't. And the only light getting through will be the light that does in fact move in that certain direction. Polarized sunglasses prevent light from entering because it polarizes. It only lets in light at a certain direction. Since the intensity of the light is proportional to the square of the field, we talked about that already, right? The intensity of transmitted light is given by this. And essentially, this is saying I naught is the original intensity, and I is the intensity after you polarize it. And then cosine squared theta, theta being the same theta as shown here at the polarizer, which is the angle between the vertically polarized light and the direction of the polarizer. And essentially what this is saying is, right, if you know cosine is is 1 at 90 and 0 at 0. So if you line up your polarizer with the original light, as shown here, if theta brought all the way up to 90, all the light would get through, you'd have the same amount of intensity. If theta was pulled all the way to the bottom, technically none of the light would get through, no percentage of that vertical polarization would get through, and you would get no light through. In lab, you can use, maybe you did this in, well, not if you took physics in high school, but you can do this in lab by taking two polarizing sheets, putting them over each other, and then rotating the sheets until eventually things get darker and darker and darker. And when the sheets are 90 degrees from each other, it's black, you can't see through it. And then as you rotate the sheets up again, you get more and more light, and eventually it just looks like a piece of glass. So again, you can see a YouTube video of this if you don't believe me. You can just do it with your hands, spread your fingers out, put them on top of one another, and then rotate your fingers, and you're going to see that eventually things are going to eventually not be able to get through anymore. If you want to do that with your hands, I guess. Unpolarized beam will pass through the polarizer, and the transmit intensity will be less than the initial, usually half, as shown by this example down here. And we can take a polarizer and an analyzer, shown here, to provide you with a final transmitted beam that is an exact intensity given by the transmission axis of the analyzer and the transmission axis of the polarizer. If you have a beam coming in with an unknown intensity, or rather a not what you want intensity, I'll say, you can use polarizing lenses at certain angles to give you a beam that you exactly want. This is essentially how a laser works. A laser produces a beam of energy that is at its production not necessarily known, and this beam of energy goes through various lenses to be fine-tuned to exactly what you want it to be. If you shoot a laser and you don't have some sort of polarizer, some sort of device on it to clamp down the beam to give you what you want, the laser just spreads like random and doesn't provide you a significant advantage, right? The laser pointer that you play with your cat is not nearly as strong as an industrial scientific laser for that exact reason, because the laser pointer you play with your cat has that little plastic cap on it. That's the only thing directing the laser light. So here's an example for everyone. Let's say you have an unpolarized incident beam coming in, I naught, shown there on the left. It goes through a polarizer and an analyzer, and it comes out at 0.2 times its initial intensity. What is theta on the analyzer to give you that amount of intensity at the end? So however strong the beam was when it started, when it entered this polarizer, it came out at 0.2 of it. What does it need to be? Essentially, I'm asking you for theta, shown here. Theta, theta. I'm asking you for solve for theta. What can you do? Well, we drop the intensity from its original intensity to 0.2. We know that the polarizer here halves the intensity, right? So between the polarizer and the analyzer, we lose half of our intensity. From this point here, between the polarizer and analyzer to after the analyzer, we go from half intensity to 0.2 intensity. 0.2 is equal to a fifth. So how do we go from a half to a fifth? Well, equation shown here in the center, a half times x equals a fifth. What is x? X is 1 divided by 2.5. Meaning, the analyzer needs to take whatever the initial intensity was before it and cut it down by 1 over 2.5 to give us our final result, which is what's going on in our equation here. I tried to do little knots, this I with a with an O, lowercase o at the end is supposed to be I naught. Again, Google Slides sucks for writing equations. I'm sorry. But what we can do is we can plug this I to I naught into the equation for after the analyzer through the polarizer and solve for theta. So I of I naught is going to equal 1 over 2.5. So if cosine squared of theta is equal to 1 divided by 2.5, just take a square root, cosine inverse, you find out that theta needs to be about 50.8 degrees. Meaning, you take unpolarized beam, send it through a polarizer, set this other polarizing filter to 50.8 degrees off of the transmission axis of the original polarizer, so theta 50.8, the beam coming out at the end of all this gobbledygook and malarkey is going to be 1/5 the original intensity of the beam. So if you have some sort of device, some sort of medical care, you want to use a laser to do something to your patient, you don't want the laser to burn them, you just want the laser to burn what it's supposed to burn. You can set these devices up to provide you with the amount of energy coming out of this beam to do what you need to do. Very useful in bioterms. And here we go, LCDs, liquid crystals. This has been an example of use shown here. Cool story. Unpolarized light can be partially completely polarized by scattering from atoms and molecules, which act like small antennas. If the light is already polarized, the transmission will depend on its polarization, right? So if you don't have radiation, everything's sitting the same way. The atoms and molecules surrounding it don't act anything special. But if we look over on the right side here, you have some sort of molecule releasing energy. The energy is only really going to go through at full intensity in certain degrees, in certain directions related to the polarization. So notice A here has essentially full energy coming out because it is parallel to the beam. B, perpendicular beam, has the least amount of energy, and C, which is between A and B, has energy going through it equal to between A and B. The arrows aren't quite as long on the east and west sides, but are very long on the north and south sides for C. If you understand the concept of polarization before, this should make sense. Sunlight can be polarized depending on the angle or line of sight makes with the direction of the sun, right? If you don't look at the sun, it's not as bright. Duh. Transmitted light is unpolarized and mostly red, but scattered light is polarized and mostly blue. Cool. I don't want you to look at the sun to test this. Don't do that. That would not be a good move on your part. Yeah, cool. There you go. That's chapter 25. Quick overcap of things we've talked about. Electromagnetic waves are traveling waves of oscillating electric and magnetic fields. They follow the right-hand rule, which is cool. Any accelerated charge emits electromagnetic waves. Electromagnetic waves follow the speed of light because light is an electromagnetic wave. Okay, Doppler effect occurs naturally. There's a different spectrums. We have categorized the EM spectrum into radio, micro, infrared, visible, ultraviolet, X-ray, and gamma ray. That you can subdivide those further depending on what you do with the EM spectrum. You can determine energy densities of EM waves, considering essentially potential energy of electric and magnetic fields, something we've talked about in class already. You can use these relationships and these intensities to determine energy at a specific point. You can also use it with momentum and pressure. Again, we talked about literally sailing through the stars on waves of energy. And polarization is a thing that's cool. Cool. That's it for the chapter. Shoot, either type in the comments or shoot me an email how this went. If this sucked, I can think of another way to go about it. I'm going to try to put this on YouTube so you can look at it again. I'll shoot you guys an email if I can figure out how to do that. I should be able to. We'll see. There is a chapter 25 homework due. Make sure to get on top of that. And I think that's good. So thanks for coming by. Again, shoot me an email of things I should do better. This is my first Zoom lecture. I don't know how it went. Hopefully it went stunningly beautifully, but I'm sure it didn't. And I guess take care.
I thought it went pretty good.